All right, team. So we are working on the last section of the probability and statistics chapter. And in this section, we're going to be learning about the very important and massively useful concept of variance and standard deviation, which are sort of a paired measures of probability distribution. So we're going to be learning about the variance and the standard deviation. So what is the variance? Let's start with the variance. So variance is a measure, and it measures how spread out or dispersed the data is around a mean. So you have a set of data points, you calculate the mean for that data, and then you're interested in how spread out is the data relative to that mean. Okay. The measure of how spread out it is the variance. So I drew this little picture here just to give you a sense of what I mean by spread. So here you have three different probability distributions: the yellow, the green, and the red. And all three of them have the same mean, mu. Remember, this is the Greek letter mu, which stands for mean. So they all have the same mean, but they have dramatically different shapes. The red one is very tightly clustered around its mean, whereas the green one is a little bit more spread out relative to its mean, and the yellow one's very spread out relative to its mean. So while all three of these probability distributions would have the same mean, they would all have different variances. Okay, so the variance measures how spread out the probability distribution is. Okay. So let's look at the mathematical definition for the variance. So if we start with a random variable x, and we know its values are x1 through x capital N, and each of these values has a corresponding probability of P1, P2, up to P capital N. And we know that the mean or expected value for this random variable is mu. Then the variance is calculated by taking the difference between each individual value and its mean, then squaring it, then multiplying by the corresponding probability. We do that for each data point and then add up all those results. And after summing all of them, we get the variance. So again, take the value, subtract the mean, square it, multiply by the probability, do that over and over and over again, and add them all up, you get the variance. So let's look at an example, how to do this computation. So in this example, you've been given a frequency table, or really a probability distribution, and we're being asked to compute the variance. Okay, so for this particular distribution, we have four values: 0, 1, 2, and 3, and these four corresponding probabilities. Now, to calculate the variance, we first need to calculate the mean. So the mean, or expected value for the random variable, we learned, is simply the value times its probability, and then you add those all up. Okay, so take all those values, multiply by their probabilities, and add them up. And we get an expected value of 1.6. So this is our mean. Now, once we have the mean, we can now build a table that will help us calculate the variance. How does this table work? So first, we start off with the values that the random variable can take on, then the corresponding probabilities, and then we look at the difference between the value and the mean. So we first compute all of those differences. So 0 minus 1.6, for instance, is negative 1.6. 1 minus 1.6 is negative 0.6. 2 minus 1.6 is 0.4. And 3 minus 1.6 is 1.4. Okay, so that's the difference between the value and the mean. Now we're going to take all of those values that we computed here, and we're going to square them. So we're going to square each individual value. So for instance, we take 1.6. I don't care about the negative now that I'm going to be squaring it, because the negative will go away. I square 1.6 and I get 2.56. I square 0.6 and I get 0.36. I square 0.4 and I get 0.16. And I square 1.4 and I get 1.96. Okay, so now we've taken everything in this column and we squared it. Now we're going to take everything in this column that we just computed and we're going to multiply it by the probability. So we'll take 2.56 and multiply it by 0.1. See if I can fit this in. Let me scoot this up. Scoot that up, and then we can do this. Perfect. Okay, so we're going to take 2.56 and multiply it by 0.1. Oops. That gives us 0.256. Then we'll take 0.36 and multiply it by 0.3. That gives us 0.108. Then we'll take 0.16 and multiply by 0.5. That gives us 0.08. And then finally, we'll take 1.96 and multiply it by 0.1. And that's 0.196. Okay. So once you fill out the table, in order to compute the variance, all you need to do is add up all the values in the last column. So the variance of this random variable x should be equal to 0.256 plus 0.108 plus 0.08 plus 0.196. So we add all of those up. 0.256 plus 0.108 plus 0.08 plus 0.196. And we get 0.64. Okay, so that is our variance for this probability distribution. Okay. Okay, so one thing I want to go over really quickly is how we might do this table procedure in a little bit neater way using the calculator. So I wanted to go over how one would go about doing this with the calculator as opposed to doing each input by hand. So this might be useful to some of you. Some of you might want to skip over this for whatever reason. It's up to you, but I wanted to show you this anyways. So I'm going to make this table on the calculator. So where I start is I hit the stat button. I hit the stat button, and that brings up this menu. I'm going to choose the very first thing that comes up. Okay, you want to start off at L1, and if there's anything in there, then just scroll up, highlight the name of what we call a list, and clear it all out. So hit clear, don't hit delete, hit clear to clear everything out of the list so that you have all of them at your disposal. Okay, so this is hopefully where you're starting off. You have clear tables, and you're starting off with L1. Okay, so here you're just going to want to put in the values: 0, enter; 1, enter; 2, enter; 3, enter. Cursor over and then put in the probabilities: 0.1, 0.3, 0.5, enter; 0.1, enter. So I'm just duplicating the tables. Okay. Now here's where things get a little bit different, but this is cool. So instead of computing each of the x minus, so remember what we're doing, we're making this table here. So the next thing we did was we took the value and we subtracted the mean away from it, right? And we did that all by hand. So now I'm going to have the calculator do it for us. And the way I do that is I go up to the L3, I cursor up and highlight that L3. And then what I'm going to do is I'm going to say, take the first list and subtract away the mean, which we've already calculated before we ever started doing this process, right? So we already know what the mean is. So what we need to do is, I'm trying to get everything visible. I'm going to hit the second button, and then I'm going to hit the number 1. And you can see above the number 1 in blue, it says L1. So when I hit the second button first, and then I hit the number 1, it brings up L1. And then from that, I'm just going to say subtract 1.6, because that was the mean that we computed. I hit enter, and it automatically fills in the column with all those computations. That's really cool. Now we keep going. Now we move over to the next list, and I cursor up to L4, and I say, what does L4 need to be? L4 should be all of these values squared. How do I do that? Well, I hit the second button again, and then I tell it to get L3, which I hit second number 3, which again, if you look above the number 3, can I zoom in that far? Yeah. If you look above the number 3, you can see in blue an L3. So second 3 brings up L3. And all I'm going to do is say, take L3 and square it. Hit enter, and it takes all those values and squares them. Okay. Now, what is the next thing we did? We took everything in this column, and then we multiplied by the probability. So that, remember, was in our second list. We put all those probabilities in our second list. So in order to do that, we go over to the L5. We're going to say, take L4, which is second number 4, and multiply by the second list, which is where we put all the probabilities. So L4 times L2. Hit enter, and boom, it computes all of those values for you. That's awesome. So these are the values you really need in order to compute the variance. Once you're here, you can either just add them up by hand, which is not hard in this case because there's so few values, or if there's a lot of values, you have another option. So we remember that these values are stored in the list 5. Okay, so I'm going to back out, and I'm going to hit second stat, and then that's going to bring up this menu, and then I'm going to cursor over to math, and then cursor down to sum. I select the sum function, and then I tell it to sum the 5th list. So second 5. And I do that, and it spits out the variance, 0.64. Boom. So going forward, if you have to do these computations with these tables, you can see how you can use your calculator to do a lot of this for you, so you don't have to sit there and punch all this stuff in by hand. All right. So let's look at another alternate formula for the variance. Here we're using expected values to compute the variance. And one really nifty formula is the variance is equal to the expected value of x squared. squared on the inside minus the expected value of x squared on the outside. So this is a really nice, elegant formula for computing this. So let's see how this works. So I'm using the same probability distribution as before. Here are the values 0, 1, 2, 3. And then here are the squares of those values, 0, 1, 4, 9. Now, as it turns out, the probabilities for x and x squared are the same. So you have the same probabilities for either values. So in order to compute the variance, we need to compute the expected value of x squared, which would be take these values and then multiply by their probabilities. So let me do that. Right over here. So expected value of x squared is equal to, take the values for x squared, 0, then multiply by the probability, plus 1 times the probability, plus 4 times the probability, plus 9 times the probability. So that would be the expected value of x squared. And we punch that into our calculator. Try to get out of the glare. See, the 0, 1 goes away. I'm not worried about that. 1 times 0.3 is 0.3, plus 4 times 0.5, plus 9 times 0.1. And that gives us an expected value for x squared of 3.2. So once you have this computation, we've already computed the expected value of x in the previous example. So in order to compute the variance, all we need to do is take the expected value of x squared, which was 3.2, minus the expected value of x, which is 1.6, squared, and we square that. So 3.2 minus 1.6 squared, 3.2 minus 1.6 squared is 0.64, same value. So you can see how that is kind of a simpler process, or definitely is a simpler process than doing all that long table and doing all those individual computations. But it really depends on the context. Okay. So now we can introduce the similar and sort of corresponding concept, or I shouldn't say corresponding, I should say we want to introduce the idea or the concept of standard deviation, which really is directly related to the variance, but it's just a slight tweak. Okay, so the standard deviation, which we denote by a sigma, which is a lowercase s in the Greek letter, in the Greek alphabet, is equal to the variance square rooted. So once you know the variance, you get the standard deviation for free. All you have to do is take the square root. Simple enough. The question might be, why? Why would you need to take a square root of the variance? What does that tell you? What's the use? And the use is that the standard deviation, as opposed to the variance, has the same units of measure as your random variable x. So the variance has the units of the variance are squared because the variance came from a squaring process. So the units aren't directly comparable to the units that you're measuring your random variable in. So if you take the square root of the variance, you get something that is measured in the same units as your random variable. So think about it this way. You could suppose you were taking you had a bunch of data that were length measurements. So they're all measured in inches. You compute the variance for that data, and the variance will be in the units inches squared, which isn't really useful. Those actually inches squared are area measurements as opposed to length measurements. It's hard to see how area measurements relate to lengths. But if I take the variance and I take the square root, then the units of the standard deviation, which is the square root of the variance, will be inches, just like the units for the data. So we can see how the standard deviation relates directly to the data, how what its effect is, as opposed to with variance. So that's really the advantage to using standard deviation and why it's often used as opposed to variance. But computationally, there's nothing new here. All we do is compute variance, take square root. Okay. So let's look at a specific example. Let's look at what the variance and standard deviation are for a binomial random variable. Okay, so remember, binomial random variables come from binomial trials. These are experiments where the outcome of each trial has a fixed probability of success and a fixed probability of failure. That's P and Q. There are n, lowercase n, many trials. Each trial is independent, and each trial only has two distinct outcomes. Okay, so these formulas are derived for you for a binomial random variable. The variance is given by n times p times q, and obviously the standard deviation is just the square root of the variance, so square root of npq. So let's look at an example. Here we are told that we have a random variable x that counts the number of ones out of 180 rolls of a die, of a fair die. We want to compute the mean and the standard deviation for this random variable. Okay, so the expected value, which is the mean for this random variable, remember, for a binomial, we learned this in the last section, is n times p. Okay, so we need to identify n and p. So n is 180. P is the probability of success, which is the probability of getting a 1 out of 6 options. So that's 1/6. And we should go ahead and compute Q, which is 1 minus P, 1 minus 1/6, which will be 5/6. So these are all the values that we need in order to do these computations. Now, to get the expected value, we take n and we multiply by p. So that will tell us that the expected value for this random variable is 180 times 1/6, which should be 30, I believe. Yep. Okay. So that is our mean. The variance we see above is n times p times q. So that's 180 times 1/6 times 5/6. So we punch that into the calculator. I can't really show you on the screen. 180 times 1/6 times 5/6, and make sure that's right. When in doubt, if you're using these calculators, you can write the expressions just as you would on your paper, separating them with parentheses. And this can be a safe way to know that you're doing the computation right. Sometimes you can get into trouble using division symbols and multiplication if you don't separate with parentheses. So I wasn't sure if that was computing right, but it did. Nevertheless, it's always safe to do it this way. So we get a variance of 25. We were asked to compute not the variance, but the standard deviation. So the standard deviation, we know, is the square root of the variance. So that's the square root of 25, which is 5. Okay, so standard deviation, again, directly related to variance. It's just measured differently. It's measured in a different unit of measure because we're taking that square root. And so whatever the mean is, the units of the mean, the standard deviation will have the same units, whereas the variance will have squared units. So if this is measured in inches for instance, then this will be measured, the variance will be measured in inches squared, whereas the standard deviation will be measured in inches. So we can actually more clearly understand the spread of the data from the standard deviation. What it's saying is that, one standard deviation away from the mean would be up 5 and down 5. So 35 up and 25 below. That would be one standard deviation from the mean. We can't add and subtract the variance from the mean in the same way because they're not in the same units. Okay. So there's a couple more formulas to go over. That these formulas correspond to some of the formulas we learned in the last section when we're learning about the mean for the population and sample. So remember, population and sample are this very essential dichotomy in the population and the sample are this essential dichotomy in statistics where we are often trying to understand a population via a sample because we can't actually survey an entire population. But there are ways to compute, say, a standard deviation or a variance for a population versus a variance for a sample. And it goes without saying that we could also compute standard deviations since they would just be the square roots of these values. So real quickly, for a population, the variance is denoted by a Greek letter sigma, whereas for a sigma squared. Whereas for a sample, it's denoted by the Latin or Roman letter S squared. So samples always get Roman letters, populations always get Greek letters. Now, how do the computations differ? Let's see. For the population, the variance is computed in the following way. You take the individual value, subtract away the mean, square it, do this for each individual value all the way up to capital N, and then add up all those values, and then divide, finally, that full sum by the number of members of the population, capital N. So value minus mean squared, do that for each value, add them all up, then divide by the total size of the population. Boom, you've got the population variance. The sample is computed in a very similar way, but there's some different notation, and there is a slight tweak here. So for the sample, which remember is a subset of the population, we denote it by S squared, the variance. And as far as the numerator is concerned, it's pretty much the same, except instead of using a mu, we use an X bar, which remember, these were the notational differences for the mean, sample mean versus population mean. So we take the data, subtract the sample mean away from it, do that for each of those, square them, add them all up, and then finally divide that whole sum, not by the total size of the sample, but by the total size of the sample minus 1. That's a very important distinction for samples. So samples get divided by the size of the sample minus 1, whereas populations, you divide by the entire population size. Okay, so very slight tweak there, but otherwise identical computations. Then it goes without saying, if you want the standard deviation for the population, you just take the square root of the variance, and same for the sample. So let's look at an example. Here we're going to be calculating the population variance. We're given the mean, the population mean is 3, and here is our frequency table for this particular population. So I guess we're going to say scores on a test, 0, 1, 2, 3, up to 5. And then here are how frequently those scores occurred for the population. So let's compute the variance. So just like before, we can use tables to do this. So first we're going to take the value, the xi. So the score is the xi, and subtract away the mean, which was 3. So 0 minus 3 is minus 3, 1 minus 3 is minus 2, 2 minus 3 is minus 1, 4 minus 3 is, 3 minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2. So that's 1, 2, 3, 4, 5, 6 values, 1, 2, 3, 4, 5, 6 values. Okay, then we're going to take all of these and square them. Minus 3 squared is 9, minus 4 squared is minus 2 squared is 4, minus 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Okay. Now, using the formula up here, once we have all those squared, we're going to add them all up. So that's 9 plus 4 plus 1 plus 0 plus 1 plus 4. And then we add all that up, and then we divide by the size of the population. Size of the population comes from totaling the frequency. So don't count the number of different scores. It's how many people took the test. So add up that whole column and you get 60. So that is the number you're dividing by, 60. So we put that into the calculator. Nine plus 4 plus 1 plus 0 plus 1 plus 4 equals that. Then divide by 60. So we get a variance of 0.317 or 67. 0.3167. And that's our population variance. Uh-oh. Come on.